This lecture is called Swim, Bike, Run and is going to introduce us to the concept of energy and the concept of physical work. It says the only place success comes before work is in the dictionary, and that's by the famous coach Vince Lombardi. So we want to take a look at what our expectations are for this particular lecture, and what they are is that students will be able to identify the factors that are necessary for physical work to occur. So you should know that physical work is very, very different from the concept of work that you now think of. If you say, hey, I'm going to go work on my physics homework, that doesn't mean the same thing as, hey, I'm going to go do some physical work. You need to be able to distinguish between work and power. Those terms, especially work, energy, and power, tend to be interchanged quite a lot in common vernacular, but they're actually very different. So you need to be able to distinguish between those. And finally, you need to be able to use the formulas. You have the formula power equals work over time, and you have work equals force times displacement. So that's what we want to be able to do. So let's go ahead and get started. The first thing is energy. Energy exists in many different forms. Okay, there's a lot of different forms of energy. One of the key things about energy is always conserved in a given system. So if you have a closed, isolated system, energy is always conserved. What that means is if you have 100 joules, which is the unit of energy, no matter what you do, you can split this 100 joules up lots of different ways, but it has to always add back up to what you originally started. That's called the law of conservation of energy, and you should be familiar with it a little bit, but we're going to go ahead and expand on it. It means that energy can be converted from one type of to another, so solar into electrical and those sorts of things. What you see here is you see this is a how the electricity company determines how much to charge you is in kilowatt hours, and that's a unit of energy as well that we'll talk about a little bit later. But you need to realize that whenever you have the electricity company, they're charging you for energy. They're not charging you for power, which is what a lot of people think. So some common types of energy, there are lots of different types of energy, but some of the most common ones is the first one is chemical potential energy, and that's the energy that's stored in chemical bonds. So whenever you burn something or a chemical reaction occurs, what you're doing is you're releasing this chemical potential energy. So this is the one you should be familiar with from chemistry. There's also the gravitational potential energy, which is the energy that's stored due to the position of an object relative to the Earth. So if I have a ball and the ball's on the ground, it doesn't have the ability to fall, so it has no stored energy. But if I take that same ball and I raise it above the surface of the Earth, now it has the ability to fall. So because of that, it's storing what we call gravitational potential energy. A couple other types of energy. We have nuclear. Nuclear you should also be somewhat familiar with from chemistry. It's the combination or splitting of a nuclei to release energy. So anytime something is dealing with the nucleus, it is a nuclear reaction. So that's a really common one as well. You also have radiant energy, and radiant energy we'll study a little bit later in the second semester, but it is studying the energy that's transmitted by electromagnetic waves, including light. Okay. You also have heat. Heat is the transfer of energy by objects of different temperatures. So if you have something that it's 100 degrees and something's at 0 degrees, what you'll do is you'll have an energy transfer from one to the other. And that's actually something that we'll study in the second semester as well, called thermodynamics. But for this particular unit, in addition to gravitational potential energy, we're also going to look at kinetic energy, which is the energy of movement. And it's just as simple as that. If something is moving, it has kinetic energy. And in fact, the term kinetic means to move. You also have work, which is considered the action energy. So work is kind of considered the go-between all the energies. And in fact, the definition of energy is the ability to do work, which means it's the ability to do something. You also have elastic energy, which is the potential energy due to the stretch or compression. Most oftentimes you see that with a rubber band, but you also see it with things like springs, and even atoms will vibrate back and forth whenever they're bonded to each other. So those are some of the common types of energy, and then you should be able to say, how do you go from one to the other? So in this one it says describe the transfer of energy from the sun to sugar in a plant. And what you should realize, I don't know if you know this from middle school, but at the center of the sun, what you have is you have a nuclear reaction. You have atoms that are fusing together. So you're taking hydrogens and you're combining them together, all these hydrogens together, get slammed together, and eventually they make one helium. Whenever you have a helium, that's a nuclear reaction. So we're going to say we start off with nuclear energy. Then what we're going to do is we're going to convert that nuclear energy to what we see from the sun, which is light or radiant energy. Then the radiant energy travels to the earth in the form of sunlight. It reaches the earth, and that light actually hits the leaves of the plant where they're turned into chemical potential energy. Sometimes they leave the potential out, just chemical energy. So what you see is we've converted from one type of energy to another to another. It says describe the transfer of energy as a box is picked up off the ground and set on a table. So what you should realize is that you have a box that is on the ground. It and when you pick it up, you're doing the action energy. The action energy is the work. So what you do is you're doing work on the object. When you do work on the object and you lift it above the surface of the earth, you have now stored it as gravitational potential energy. And people say, but wait a second, it's on the table, it can't fall. Well, yes, it can. It still has the ability to fall to the surface of the earth. So because of that, if somebody nudged it, it would still fall to the ground. So it's worked gravitational potential energy. And finally, it says describe the energy transfer as a car initially moving down the highway slams on the brakes. So what you have is you're initially moving. So since you're moving, you have kinetic energy. Okay, KE is kinetic energy. Now, when you slam on the brakes, you're doing work. Okay, that's that action energy. You're trying to slow it down. So you're doing work on the car. And as a result, I don't know if any of you have ever experienced this, but if you were to actually touch the brakes after you stop, they get extremely hot because all that energy is transferred into heat. Okay, so in the swim, bike, run competition, otherwise known as a triathlon, it's generally an endurance competition. It's one of those things where the person who is the most powerful, the biggest, the strongest, the fastest is not always the person that wins. And it's kind of the same thing whenever we talk about it in terms of work and power and physics. It's not the one that has the greatest force. It's not the one that moves the farthest. It's not the one that moves the fastest, but instead it's the one that's a combination of all those three things. And we're going to talk about that a little bit, but just so you know, whenever you push something that's really large, that doesn't necessarily mean you're the most powerful. Whenever you do something extremely fast, that doesn't necessarily mean that you're the most energetic. And we'll kind of talk about that as we go through. The first thing is physical work. Physical work is very, very different from the concept of work as you know it. Whenever you have a job and you say, hey, I'm going to work, that means a certain thing, but whenever you look at it in the context of physics, it could mean something very different. And here's what I mean. Physical work is the action energy that relates kinematics and dynamics with energy. Okay, physical work requires two things. You must apply a force on the object, and the object must move in that same direction. And this is why it's really important. If you were to look right here, you have the man Sisyphus, if you know the Greek legend. He is pushing this rock, and if you look at it, he is clearly exerting a force on the rock. He is trying to push the rock up here. But we cannot classify this thing as actual physical work because we don't know if he's making any progress. If the rock were to move in that same direction, then yes, we could say that Sisyphus is in fact doing work. But without that movement part of it, we can't say for sure whether or not that he is doing work. Another example says, does a person leaning against a wall do work? So you have a person, and they're leaning against a wall, and they're clearly exerting a force on the wall, but the wall doesn't actually move. So because the wall doesn't actually move, you can't say that the object or that this person is doing any work on the wall. The next thing is you have to say that the force and movement are in the same direction. So let's say that I have a situation in which I am lifting a tray or a box, okay, and I'm clearly exerting a force on the box upward, okay, because I'm keeping it up out of the air. So I'm carrying a box or a tray. But my arm, which is supplying the force upward, is my arm. The box is moving this way due to my feet. So can you say that your arm is doing work on the box? And in fact, you can't because the force and the direction are perpendicular to one another. Remember, you must have the force and the displacement be in the same direction in order for work to occur. So this is where we get the equation. The equation is work equals force times displacement. and we've talked about most of these before. We've talked about force as being a push or a pull. It's measured in newtons, and you can measure it with a spring scale. We've talked about D. D is really displacement, not distance. But on the formula chart on the tax formula chart, it actually says that it's distance, but really it should be displacement. But it is measured with a meter stick, and the unit is the meter. So one thing that you have to realize is, once again, this assumes that the force and the displacement or the distance are in the same direction. If they're not in the same direction, this formula will not work. So let's take a look at this formula in action. It says determine the work exerted on an object if it is subjected to the forces below for 10 meters. One of the things that you need to realize is that the force actually represents what we call the net force. So you can look right here, you can say I've got 50 newtons up, 50 newtons down, those cancel each other out. I've got 100 newtons right, I've got 20 newtons left. Those don't quite cancel each other out. So what I can say is that my force is 80 newtons, because you have one force to the right, one force to the left. Now, I'm going to assume that the object is actually moving in the same direction. Really, it should say, and it moves 10 meters to the right. So that lets me know that my distance or displacement right here would be 10 meters. I can use my equation work equals force times distance, and I can say 80 times 10 is 800 joules. Okay, so you need to be able to use everything that we've already talked about in terms of free body diagrams, identifying what the force actually is that's being exerted on it, because those things don't go away. In the second example, it says determine the work done on a car. It's got 1,000 kilograms, so we're going to underline what we've got. If it accelerates at 5 meters per second for 25 meters. Okay, and you may be looking at yourself and saying, okay, I'm trying to find the work, and then say, once you know that what you're trying to find, you look at what you're given. We're given a mass of 1,000 kilograms. We're given an acceleration of 5 meters per second squared. We're given a distance or displacement of 25 meters. And what we're trying to solve for is, once again, the work. So you look at your equation, you say work equals force times distance. You say, okay, well, work equals force times distance, but I don't have the force, so I can't solve this question. And this is another case of, you have to remember what you were taught before. So yes, you do not have the force, but you learned earlier that you had an equation that said that force equals mass times acceleration. If force equals mass times acceleration, I can substitute ma in for F. And what that does is it gives me a new formula. W equals MAD, or I like to remind my students that it just says that work makes you mad. It's an easy way for you to remember, work makes you mad. So whenever you do this, you can now plug in the numbers, and you would say, okay, work equals 1,000, which was my mass, times 5, which was my acceleration, times d, which was 25, which was my displacement. Whenever you take all this and you multiply it out, you should get something around 125,000 joules. One of the things that I want you to realize off the bat is the unit of energy, the joule, is actually an incredibly small amount. So when you see something like 125,000 joules, don't get nervous and say, wow, where did I get that from? A joule is a very, very, very small unit of energy. For this third example, it says calculate the force exerted on a box when it requires 500 joules to move the 10 kilogram box a total of 25 meters. So in this case, we're trying to solve for the force. Whenever you look at it, you can say, okay, well, I'm trying to solve for the force. And what I have is I've got this 500J, 10 kilograms, and 25 meters. So I would say work equals 500 joules. I would have mass equals 10 kilograms. I would have distance equals 25 meters. And you can say W equals FD. Once again, this is one of those cases in which you can go ahead and solve for it right away. People say, well, wait a second, what is this 10 doing here? I don't know what to do with that. It's actually irrelevant to the question. It makes no difference that you have the mass of the box. All you need is the work, which you can plug in, equals force times 25. Sometimes people get nervous the fact that they have too much information and that they're not solving it the correct way. A lot of times you're given extra information to see if you know what to do with it. So when you take this and divide it out, you would get the force is equal to 20 newtons. Okay. Now, if you wanted to, you could then take the force and the mass and solve for the acceleration, but that's not what the question asks us to do. It asks us to solve for the force. Now have our last part of this video, and that's the power equation. The power equation says that power equals work divided by time. So now we're familiar with most of these terms. We've talked about the term work earlier in this video that was measured in joules, and we've talked about time several times before as being measured in seconds, but that introduces us to the new concept of power. Power is the rate at which energy is transferred. Now, most of the time we say that that's power equals work divided by time, but it could actually be any sort of energy divided by time. One of the most common misconceptions about power is that it is somehow some type of energy, and it's not. It's the rate at which energy is used. So a lot of people say, oh, well, the electricity company is the power company. And they're not the power company because they're not selling you power. What they're doing is they're selling you energy. Specifically, they're selling you electrical energy, but they're selling you energy, not power. So that's kind of an incorrect term or misnomer for who provides you electricity. So let's take a look at this equation in action. It says, what is the power of a weightlifter who lifts a 200 kilogram barbell 1.2 meters above their head? The weightlifter is 1.7 meters tall and completes the lift in 0.75 seconds. So let's take a look at this. We are trying to solve for the power. We have a 200 kilogram barbell, 1.2 meters above their head, 1.7 meters tall, and completes it in 0.75 seconds. So let's go ahead and take a look at this question. We say, okay, I'm trying to solve for power, and I'm given mass of 200 kilograms. I'm given a distance of 1.2 meters. I'm given another distance of 1.7 meters, and then I'm given a time of 0.75 seconds. Now, the equation that I have for power is power equals work over time. One of the problems with this in this particular case is that I don't actually have work. I have time, but I can't calculate power from just time. So instead what I want to do is I want to expand this equation. So instead of work, I want to put force times distance over time. And that gives me a new equation. It gets me a little bit closer because I have a distance term. In fact, I've got two of them. I've got to figure out what to do with that, but not quite yet. So now I've got this force equals distance over time, but still, once again, I don't actually have force. So let's expand it a little bit further because remember, force is really mass times acceleration. So what that can give me is power equals mass times acceleration times distance divided by time. Okay, and you look at this and you say, okay, well, I've got mass, I've got distance, and I've got time, but I'm still missing acceleration. But what you need to do is you need to think about it. They're lifting the weight vertically. Whenever you lift it vertically, remember your acceleration due to gravity comes into play, and you know the acceleration due to gravity is 9.8 meters per second squared. So, because of that, you can now say, okay, power is equal to, we like to say that physics has the power to make you mad over time. It's the easy way to remember it. But now we come back to this idea of I have two distances. Remember, what am I trying to solve for? I'm trying to figure out the power from picking it up off the ground all the way over his head. So the fact that he's a certain height shouldn't matter, and the fact that he lifts it a certain distance over his head doesn't matter. I actually need the combination of those two for a total of 2.9 meters. So when I do that, I can now plug in my numbers. I can say, okay, power or the mass is 200, the acceleration is 9.8, the distance is 2.9, and we can divide it by the time, which is 0.75 seconds. Now when you take all those and you combine them, you end up getting something pretty large. It should be about 7,580 watts is what you should get. So you need to be able to take the power equation and expand the work, expand the force, and get it to what you need to be. And that's probably the trickiest thing that you can do with these energy and power equations, is that you have to expand them. The second example says, how much force is exerted by a 1200 watt engine, so I'm looking for force, by a 1200 watt engine that lifts an object 5 meters in 2.4 seconds. So we're trying to solve for force. We have the power of an object being 1200 watts. And this is something that's confusing for people sometimes because they say, well, wait a second, is that work because it's 1200 W? Remember, 1200 watts is the unit of power. If it was measured in joules, then it would be a unit of energy, so it could be work. So you've got to know those units in order to distinguish between these. You have the object is lifted a total of 5 meters, and the time is 2.4 seconds. When you take these three variables, you can now go ahead and figure out what your equation is. My equation is power equals work over time. And once again, you'll see that that doesn't actually have force in it. So what I need to do is I need to expand the equation to force times distance over time. Oh, excuse me, force times distance over time. Because work, remember, is force times distance. Now if you were to take a look at it, I've got power, which I've got right here. I've got distance, I've got time, which means the only thing that I don't have is force, which is what I'm trying to solve for. So you can go ahead and say power equals force times distance over time. We can now plug in. We would say 1200 equals force times 5 divided by 2.4. You would multiply both sides by 2.4. You would divide both sides by 5. And when you did that, you would get an answer of 576 newtons. The last example we have says determine the time required for a 60 watt light bulb. Determine the time for a 60 watt light bulb to give off 50,000 joules of energy. So we are trying to solve for time. And I have a 60 watt light bulb, so that means I'm given the power. I'm given an energy of 50,000 joules. Now remember, it can be work or it can be any other type of energy. In this case, it's probably a combination of light and heat, and that allows me to solve for time. I use the equation P equals W over T, or 60 equals 50,000 divided by T. You would multiply both sides by T to get it to the other side. Now, a lot of people want to divide by 50,000 there. You can't do that because remember, you would have T on the bottom at that point. So you multiply both sides by T, and then you divide both sides by 60. And now what you have is you have T equals 50,000 over 60, which is 833 seconds.